So today's the 11th, I think. Okay, so we decided to continue with 39 on page 299. Okay, here's the problem. Let me read what is required. Find the intervals of increase or decrease. Find the local max and local min values. Find the intervals of concavity, inflection points. In other words, everything. So the function is f of x equals x times the square root of 6 minus x. Okay, we're asked to graph a function. What do I have to think of first? Say it again. Right, but what do you really mean? I know what you mean, but what do you really mean? Say it again. Excellent. I cannot start doing anything before I find the domain of a function. Excellent. Good. So what do I have to write in order to find the domain of this function? I have to write something, solve it, and then I will find the domain. So, yes, what do I write? Perfect. Great job. Excellent. So the quantity under the square root must be greater than or equal to 0. Would you agree? Everyone. Okay. So therefore, negative x greater or equal to negative 6, x less than or equal to 6. So here's the domain, negative infinity to 6. Any questions on the domain? Any questions on the domain? Please create this table with me in which we will organize and summarize everything we find about this function. Everything. So here's the first thing I have to put in the table. Is that clear? We established the domain of this function is negative infinity to 6. So then negative infinity to 6 is all I need to see and look at. Nothing else. Okay. I would like to see what happens at 6. Can anyone give us the value of the function at 6 so I can write it in here in the row for the function? 0, very good. Perfect. Now I would like to determine where the function is 0. And you can say at 6. Yes, but there is another chance for the function to be 0. So y equals 0 means x, the square root of 6 minus x equals 0. And there are two options. I hope you agree. One option comes from x equals 0, and the other option we already established comes from x equals 6. So then somewhere in the middle, I put 0, and I put 0. So this function has two x-intercepts. It happens that this is also the y-intercept, because if I want to determine when x is 0, I get y equals 0 already. So I determined the x and y intercepts. I need to determine one more thing, which is this. What am I saying to you here? What am I asking you to find? Excellent. The limit at negative infinity as x approaches negative infinity. Thank you, Savannah. Awesome. So limit from x, the square root of 6 minus x, as x approaches negative infinity. Let's do this together. Ready? Where does this go when x approaches negative infinity? There's a minus in front. Right? So I would be in big trouble, because if this is negative infinity, I cannot take the square root from it. Right? So negative times negative infinity is positive infinity plus 6 is still positive infinity. The square root of infinity is infinity. Multiplied by negative infinity, the answer is so this approaches negative infinity. This approaches infinity. When I multiply negative infinity by infinity, I get good. Perfect. There is nothing else I can find about the function from the function itself. That's all I can determine. X and y intercepts and limits. Okay? Nothing else. That's all I have. Moving on. I need to determine the first derivative and study the sign. Of course, not before I find the critical numbers. So f of x equals x the square root of 6 minus x. I need to find f prime. Okay, I need anyone to dictate. Very good.
1 over 2 square root of 6 minus x.
So careful. So this is the first function, and this is the second function. The first function prime is 1 times 6 minus x plus the first function times the second function prime, 1 over 2 the square root of 6 minus x, and that's not enough. Excellent. Excellent. Great job. I see two fractions. I have to find a way to combine them under one fraction line. I have to. So this is over 1. I will clean this up a little bit, and then you will give me the least common denominator. So the square root of 6 minus x divided by 2, the square root of 6 minus x. Please, anyone determine the least common denominator. There is only one. Right. 2 the square root of 6 minus x. So this one needs to be multiplied by 2 times the square root of 6 minus x. Can anyone dictate this product? 2 parentheses 6 minus x. Minus x. Great job. So this is 12 minus 2x minus x divided by 2, the square root of 6 minus x. Always remember, clean it up. I don't want the negative leading coefficient. So this is negative 3x plus 12 over 2, the square root of 6 minus x. I will factor out negative 3, bless you, and then I get x minus 4 at the top to 6 minus x. This is extremely important. Remember, when we looked at, as I said, I will post the solutions to the test tonight. So I just wanted to point out this problem H, right, with all those little things. So this is the simplified form. I was very happy to see not enough of you came up with this, but who came up with this was so nice and clean. I was just my dream. Check and move on. That's my dream. Okay, so you understand that this is a whole kind of messy, but once you get here, then you can determine the values for which f prime is 0, or the critical numbers, very easily. X equals 5/2 and x equals 14. Otherwise, from the very beginning, you will not be able to solve this equation as f prime being 0. That's why simplifying is so important for chapter 4. That's why we did this. But as I said, some of you presented this so clean, amazing. Well done. Good job. Okay, so that's why I simplify the derivative as much as I can, because now when I write this or this to find critical numbers, then it's straightforward. I don't need too much work. So let's see if this function has critical numbers coming from any or both of the sources. Okay, so is this function, which is this function, ever 0? Always remember, a fraction is 0 only when, exactly, right? So see how easy it is to see when the numerator is 0? When is the numerator 0? Exactly. So from here, I have x equals 4. What about from here? I'm looking for x values for which this function is undefined, but the original function is defined. If they are both undefined at that value, that's not a critical number. But if this one is undefined at 15, and the original function is defined at 15, 15 becomes a critical number. So let's look at this as well as the original function. This was the original function. So x equals 6, do you agree? X equals 6, this function is defined at x equals 6. But is this function defined at x equals 6? No. Very good. So then, x equals 6. Both 4 and 6 are critical numbers. Now I'm going back to the table. I will have to insert 4, put 0, and at 6, specify that it's undefined. If the first derivative is undefined there, all the other ones will be undefined as well. We are only interested in the second one. Okay, now I have to study the sign of this function right here. So let's go back to the first derivative. Here's the first derivative. For the purpose of the sign, I will disregard these. Why will I disregard those? Just for the purpose of the studying of the sign. Why would I disregard these? Because they are positive. Positive. Whatever quantity is positive is not going to change anything. So all I'm interested in to find the sign for is negative x plus 4. So let's go to the left-hand side of 4, plug in 0, and give me the sign of this expression. Yes, it is positive. Excellent. Now let's plug in 5, which is between 4 and 6. Please plug in 5 into negative x minus 4 and give me the sign. Excellent. That's all I need. I have to determine the function value at 4. So let's plug it in. So f of 4. How much is f of 4? F of 4 is 4 to the square root of 6 minus 4. So this is 4 to the square root of 2, and I have to approximate it. So this is 1.41, roughly, what is it? Is it 5.64? So I'm going to write 5.64. Now the moment of truth. These two rows have to work well together. If they don't work well together, then I would say, oops, I have an error somewhere. Ready? Okay. The function comes from negative infinity to 0. What does the function do? Increases. Is that supported by the sign of the first derivative? Yes, because we established that when the tangent has a positive slope, in other words, when the derivative is positive, the function is increasing. Okay, so increasing, and from 0 to 5.64. Is that supported by the sign? Now from 5.64 to 0, what does the function do? Is that supported by a negative sign for the derivative? Okay, very good. Now let's establish one thing here. This function has a critical number at 4 because the derivative is 0. Has a critical number at 6 because the derivative is undefined when the function is defined. My question is, what type of point is this? From positive, 0 to negative. Positive slope, 0 slope, negative slope. What type of point is 4, 5.64?
Max.
Yes, it's a local max. Local max, for sure. Now, what's going to happen here? I don't know. We'll see. We'll draw a conclusion about 6, 0. Okay? It can only, since at the end of the interval, it can only be an absolute min or an absolute max. It cannot be local. The function doesn't exist on this side. So I don't know. We'll see. We'll draw a conclusion later about that point. Okay, now at this point, we are discussing the second derivative. So here is our first derivative. So f prime is negative 3 x minus 4 divided by 2 the square root of 6 minus 4. Now I have to warn you that differentiating this, it's not going to be a simple situation, because I have a ratio and I have a radical in the denominator. But of course, I will take those constants out. They are in my way. I don't want them there. So, prime, of course, I didn't differentiate yet. So this is negative 3/2 times. Can anyone differentiate the top for us? Very good. Times the denominator. Minus the numerator times. Can anyone give us the derivative of the square root of 6 minus x?
1 over 2 6 minus x times negative.
Excellent. And now please square the denominator and give us the denominator.
6 minus x.
Indeed. Good. I'm going to clean it up a little bit. And let's address the numerator. That's where the problem is now. The square root of 6 minus x, but now plus x minus 4 over 2 the square root of 6 minus x. Like before, I need the least common denominator in the numerator. Yes, Vanessa, I'm sorry.
Are you doing the f over g? Wouldn't the g have to be squared?
So let me refresh your memory. 1 over 2 prime is 1 prime times 2 minus 1 times 2 prime over 2 squared.
Yeah, that's that. I didn't see where you have it there.
So the square root of 6 minus x squared is 6 minus x.
Oh, okay.
Better?
Yeah.
Perfect. I lost track of pages again. Sorry. Okay. Good. The least common denominator, please.
2 is 6 root x.
Very good. So then this one needs a 2, the square root of 6 minus x again. So it's 2 parentheses 6 minus x plus x minus 4. This is not a simple situation. It's not. It's a lot of work. It's very easy to lose track of the next step. Very easy. Okay. Negative 3/2. So now I'm going to flip the denominator. So I have 2 6 minus x, the square root of 6 minus x. And now the numerator. 12 minus 2x plus x minus 4. I need to caution you on one thing. One of the reasons why in my table I put the second derivative last is because sometimes it's so difficult to get it that we may be able to make the necessary adjustments or graph without it. Sometimes we determine it and nothing comes out of it as well. So that's why I like to leave it as the last row. But we will always try to find it and study it. Okay, so what is left at the top? So it's a negative x plus 8, right? 3/2, negative x plus 8, 2, 6 minus x, the square root of 6 minus x. And now I'm going to factor out negative 1. Always remember, simplify factor, remove negative leading coefficients, descending order. This should be always the case. 3/2 x minus 8 divided by 2, 6 minus x, the square root of 6 minus x. Okay. So now we're trying to find if this function has inflection points. So the second derivative set equal to 0. It's undefined at the same value where the first derivative is undefined, so there is nothing there. And for the second derivative, we only need when it's 0. Okay, so what do we get? X equals 8. However, I cannot put it in. 8 is somewhere here, right? I can't put it in. It's not in the domain. So that's why I said, don't get upset. Sometimes the second derivative may, however, I still have to study the sign of the second derivative. And I will tell you, or this time I would like you to tell me in which portion of the second derivative you will not plug in numbers, for sure. Which one? In this whole thing. Why I refuse to plug in numbers in here? Because I already stated the restriction from the first thing, that 6 minus x is positive. That 6 minus x is positive, right? That's how we started. I'm not going to waste my time. All this part is positive, but I will have to study the sign of x minus 8. So please plug in anything you like, because 8 is on this side. Plug in anything you like and give me the sign of x minus 8. Would you agree? Very good. What does that mean? It means that this function is concave down everywhere. So when the second derivative is always negative, the function is concave down. If the second derivative is positive, it will be concave up. What if it changes sign? If it changes sign, that's an inflection point. But it doesn't change sign anywhere. The function is opening downward. That's all the information I need. And now I'm ready to graph the function. I don't care. I'm just making a point. I don't care about anything but this. All my information is here. Everything I need and everything will help me graph this function is in this table. I don't need to look back at 5 pages of work. That's all I need, this table. So let's draw the coordinate system. Let's plug in the points we have. 0, 0, 1, 2, 3, 4, 5, 6. So one more time. Ready? I have the point 0, 0. I have the point 6, 0. Now I have to plot the point 4, 4, comma 5.6. 1, 2, 3, 4, 5, 6, 7. So 2, 4, 5.6, and 4. Ready? The function comes from negative infinity. It's increasing, opening downward till the x-intercept. Okay. One more time. Coming from negative infinity, increasing to the origin, opening downward. It continues to increase to this point, which is a local max. Still opening downward. At this point, still opening downward, it starts to decrease to 0.6 comma 0. This is the graph of f of x, x the square of 6 minus x. According to the graph, I will say that this point is nothing. It cannot be local. It cannot be absolute. Why? It's at the endpoint of the interval. It's not an absolute max or min because there are other values higher and lower. This turns out to not only be the local max, but also the absolute max. If you want to check with the graphing calculator, we can do that. So with the graphing calculator, you can put it in. My apologies, I forgot to get my calculator. So please put in x, the square root of 6 minus x. I just want to change that already. Okay, y equals, so x, the square root of 6 minus x, close the parenthesis. And I want to adjust the viewing window because I graphed the function. So I only want -4 4 to 8, and between negative 10 to 10 is fine. Okay. Okay. So I see the graph is all the time concave down because the second derivative is negative. It's coming from negative infinity, crosses the origin. It reaches the point that we know it's 4, 5.64, and it continues to decrease to the endpoint of the interval of the domain, 6, 0. You know that this is an error. The function doesn't stop here. You know what the function is doing. You know more than what the calculator is showing. Any questions here? So you understand, I am not forcing you to use this table. Create your own, whatever type of table. But if you don't summarize the information, you will have difficulties, or it will be more difficult to come up with the correct graph if you have everything all over the place. Now, I'll show you, I think I did show you last time, and I'll show you one more time. Here is what the book is doing. I totally disagree with it. Absolutely, totally disagree. They say blah, 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 blah. Here's the graph. But how you put all this together, how you show, and how from here you get this, I have no idea without summarizing the information. Okay. Other questions or any questions for me here? Anything? So create your own table. I will not take credit for the table. One of my professors showed me this table when I was your age. Okay, so I will not take credit for it. Any questions? Any questions? I would like to look at a problem in which we analyze the information given and we come up with a graph. Please choose. I would like to work like we always do on these kind of problems. We are given, sketch the graph of a function that satisfies all of the given conditions. So please choose a problem, or I will.
24.
24. Okay, very good. So we want to look at 24 on page 298. It says a vertical asymptote x equals 0, f prime of x greater than 0, for x less than negative 2, f prime of x less than 0, for, I'm just copying the information, I didn't summarize anything, x greater than negative 2, and of course x not equal 0. Next condition, the second derivative is less than 0. For x less than 0. And the second derivative is greater than 0 for x greater than 0. So these are all the conditions given to us in problem 24 on page 298. You know what I'm going to do, right? You already know me. What am I going to do? The table, excellent. Summarize all my information. I have no idea what to do with this. But after I summarize it, it will be crystal clear. Crystal clear. Ready? We are told that x equals 0 is a vertical asymptote. No problem. It means that the function and its derivatives are undefined. I may be told, I don't know, that these are, I don't know, I'm just putting question marks, but that's what it means. If I'm told that x equals 0 is a vertical asymptote, at least one or the other must be on the one side, or the other must be, or both, must be infinities. Positive infinity, I have no idea yet. That's why I put it in there so I don't forget, but with a question mark. So this is done for now. The first derivative is positive for x less than negative 2. Negative 2 is here. I don't know what happens here. I'll come up with a conclusion in a moment. But this first derivative is positive to the left of negative 2. So this is taken care of. The first derivative is negative for x greater than negative 2. Okay. This is done. The second derivative is less than 0 for x less than 0. Okay. Less than 0 for x less than 0. This is done. And it's positive for greater than 0. I took everything into account. I created this table. Now, what does this mean? It means that definitely the function must open downward to the left of 0. It must, we also like to say, it holds water or it doesn't. So it's concave up on the right-hand side of 0. What else do I learn from here? If the sign changes left and right of negative 2, I'm going to come up with a number, whatever you want. We can make up the rest. This is going to be an example. So I'm going to say this is 4. So because it's opening downward, I'm going to say, and it's very clear, it must be increasing. This is increasing. It must be decreasing. Obviously, it cannot be, if I choose this to be 4, this cannot be a positive infinity. So I'm going to make it negative infinity. Here, the function is opening upward. It's decreasing. It must be coming from positive infinity. I'm going to make this 3. So it's decreasing towards 3. From positive infinity to 3, and it opens upward. And now I have everything I need to graph an example of such a function. There is more than one correct answer here. So I created this point, negative 2, 4. You can create any other point. You don't have to stick with negative 2, 4. Opening downward, increasing to this point. And since x equals 0 is a vertical asymptote, my graph does this. So it's coming or increasing. You can put here, if you want, negative infinity. You can make up anything else as long as you use what is given. And now my graph, for whatever reason, has a horizontal asymptote at 3 on the right-hand side. It's coming from positive infinity, decreasing, opening upward towards 3. And this is my example of a function that complies with all the given conditions. You can make it up your own. It doesn't have to be this one, as long as you keep in mind what was given to us. Any questions? Yes, Vanessa, please.
I'm not really sure how you got 3.
Oh, I just made it up. This one here?
Yeah.
I just made it up. You can put 0, and then your horizontal asymptote would be this. Or you can say, I don't want to put anything. That's fine. I just thought it would be interesting. A function like this with a horizontal asymptote on one side and no horizontal asymptote on the other side. But you can change the graph the way you like. As long as it's opening upward, you don't have to create a horizontal asymptote. Here I wanted to create y equals 0 horizontal asymptote. I'm sorry, you know what I meant. And I didn't mean 0, I meant 3. Yes, any questions? Okay. We did talk about L'Hopital's rule. And I just want to go through more examples. And this is our next section in 4.4. So I'm happy that I did not wait, because now we are short for time. So 4.4, L'Hopital. L'Hopital's rule. L'Hopital's rule. Can anyone refresh our memory on how many different indeterminate cases we had? So we have a total of 7. Total of 7. We have not encountered all of them. We have encountered infinity over infinity. I hope you agree. We have encountered 0 over 0. And these are the only ones that work with L'Hopital's rule. The only 2. And we looked at also infinity minus infinity. 7 indeterminate cases. Okay? They're not undefined cases, indeterminate. Indeterminate cases. Okay, so there are 4 more. Okay, on page 308, let me refresh your memory. When do we use L'Hopital's rule?
When the limit ends.
Exactly, only for limits. Only for limits, and only for these 2 cases. Very good. So let's practice with some limits. On page 308, 24 caught my eye. Please feel free to choose. 24 on 308. Limit as u approaches infinity from e to u over 10, everything divided by u to the 3rd. We're asked to find this limit. What is the first thing we do when we are asked to find the limit?
Plug in that.
Plug in. Very good. When u approaches infinity, where does this go?
Infinity.
Excellent. E to infinity. Infinity. Very good. What about the denominator? Good. I like it. Why? Because it's one of these cases in which I can apply L'Hopital's rule. That's number 1. Number 2, even if it's one of the other ones, I may still be able to change them into one or the other, so I can apply L'Hopital's rule. But here, there is no work necessary. It's already infinity over infinity, one of the 2 allowed. Perfect. And that reminds me of, I saw on your test, you differentiated, it's a different problem, but something like x squared divided by, I don't know, e to the x as the quotient 2x over e to the x. Can I do that? No, because this is the quotient rule, right? So please remember, please, do not confuse. This is allowed, but only in a limit, only inside a limit, and only if we have infinity over infinity or 0 over 0. Otherwise, this is never allowed. Okay, perfect. Good. So let's differentiate the top. So I can differentiate. Do not drop the limit operator, as we remember, please. So let's differentiate the top. What do we get? Yes? E to u over 10 times? So one more time. U over 10 is the same with 1/10 times u. So when I differentiate this or this, I get, when I differentiate this or this, what do I get? When I differentiate 1 over 10, a constant, times u, what do I get?
U to the 10.
Say it again.
U to the 10.
Why? Why? So when I differentiate the constant times the function, I have the constant times the function prime. So what do I get?
1/10.
Thank you. Of course. It's like 1/10 x. It's 1/10, right? So e when I differentiate this, e to u, or e to a function prime, is e to the function times the function prime, which is 1 over 10. Yes, everyone? We agree? Okay, the denominator, please.
U is 6.
Careful, not to confuse with the quotient rule. Okay, we forgot L'Hopital's rule then.
U squared.
Exactly. Yes. So when we differentiate inside the limit, only then, and only if we have infinity over infinity or 0 over 0, we differentiate the top as if it's alone on the planet, and we differentiate the bottom as if it's alone on the planet. It's only the only case in which we can do that. Good. So now I'll take 1 over 10 over 3 outside, 1 over 30. I don't want it out there, in there. It bothers me. So e to u over 10 over u squared. Good. So plug it in again. What do we get? At the top, where does it go?
Infinity.
Where does the bottom go? Good. We apply L'Hopital's rule again. So 1 over 30 stays outside. So limit as u approaches infinity. So please give me the derivative of the top. E raised to u over 10 times 1/10, indeed, divided by the derivative of the denominator.
2u.
Excellent. Okay, again, 1 over 10 divided by, or flipped 1 over 2 is 1 over 20, times 1 over 30 is 1 over 600, limit u approaches infinity, e to u over 10 over u. Okay, what is it now? Where does the top go? Excellent. Where does the bottom go? Yes, because u approaches infinity. Awesome. So then 1 over 600, limit u approaches infinity. The derivative of the top, please. U over 10 times 1 over 10, and the denominator prime is? Excellent. So now I have 1 over 6,000, limit u approaches infinity from e to u over 10. Where does this go? Good. How much is infinity over 6,000? Very good. Uh, 36. Any questions? Any questions?